All right, good afternoon. We're going to get started with our 1:30 press conference. Another giant polar cyclone, Juno science results since jumping Jupiter's shadow. Our first speaker will be Steve Levin from NASA's Jet Propulsion Laboratory. We also have Alessandro Mura from the National Institute for Astrophysics, Cheng from Caltech, and Candice Hansen from the Planetary Science Institute. I'm going to turn it over to Steve to get us started.
Thanks. So we're going to tell you a little bit today about some new exciting news we found about a new circumpolar cyclone joining the club at south of Jupiter. And we're also going to tell you about how the spacecraft survived to be able to tell the tale and feature a few of our spectacular images from JunoCam as well. One of the very first things we discovered at Jupiter was that the poles don't look like the rest of the planet. So here's a JunoCam image. This is actually the new one. What we found at the South Pole was 5 circumpolar cyclones, 5 storms, giant storms 7,000 kilometers across around the South Pole with one in the center. And as you can see now on our latest image, now we have 6. So we were there in 2016, we found these 5. We've been watching them every 53 days as we come by close to Jupiter in our 53-day orbit. And each time there were 5. Once in a while, it looked like maybe there was a cyclone trying to muscle its way into the club that got pushed off. And then finally, in our most recent Perijove pass, we see now there's 6. So you'll get some beautiful images of this from Alessandro later and some pictures from Candy. But first, I want to tell you a little bit about how we managed to have the spacecraft survive to be able to do that. So, as I hope you know, Juno is a solar-powered spacecraft, which means we need sunlight to get power. And we were in danger, if we didn't do anything, of going into the shadow, going into eclipse by Jupiter, being in the cold and dark. And solar-powered spacecraft don't like to be in the cold and dark without any power for heaters. The spacecraft would have frozen. What happens is, if you look down at the bottom of that chart, when we first got to Jupiter, we had our orbit set up so that it's crosswise to the direction to the sun. So for the entire orbit, the spacecraft is in the sunshine and everything's fine. But as the years go by and Jupiter moves around the sun, effectively the position of the sun is changing. And so there was a time in November of this year where it looked like we were going to go into a 12-hour eclipse. And in 12 hours, the spacecraft, without any sunlight to power the heaters, would have gotten cold, really, really cold. So we were, of course, very concerned whether it would survive at all. We looked at how could we make it survive that long a time. We looked at what would it take to push the orbit around so that it lined up with the sun, which would take lots of fuel. We needed a creative, smart solution. And fortunately, the navigators at JPL specialize in brilliant creative solutions, and they came through once again and found a way to save us. So this is what we did. First, what you can see, this is now looking at Jupiter with the sun behind it. So you're out in the shadow of Jupiter in the eclipse, and you're going to see our spacecraft come by in this animation. And as you see, on one Perijove pass, we miss the shadow just barely. And then if we didn't do anything and we waited 53 days out to the end of the orbit, when it comes back the next time around, what you'll see is that the spacecraft would have gone right across the shadow, 12 hours in the cold, and we'd be dead. So we needed a way to avoid that. And what the navigators came up with is when it's far from Jupiter, if you fire the thrusters a little bit and sort of twist the orbit off at an angle, we can make it so we just miss the shadow on the other side of Jupiter when we come by the second time around. So you can see that here in the animation. There it is. So we fire the thrusters for a long time, for 10 hours. So what's happening is they pulse as the spacecraft spins every time they're pointing in the right direction. So you see those little pulses, and you see the red picture of what the orbit would become. The longer you fire them, the more you get to push that off to the side until finally we got to where we were safe. So Without that maneuver, without the creative genius of the folks at JPL on the navigation team, we wouldn't have the beautiful data that we have to show you today. And I'm going to turn it over to Alessandro Mura, who can show you some amazing images in the infrared and talk about the new circumpolar cyclone that we found.
Thank you, Steve. Okay, so Durham is a Jovian infrared auroral mapper. It's an instrument founded by the Italian Space Agency, and it's basically a camera, but in the infrared. So a usual camera, a common camera, works in the visible light. And in the visible light, you need a very hot light source, such as the sun or a light bulb, to illuminate everything. And everything is just reflecting those light. Actually, in the infrared, however, everything is emitting its own light. That means that what is dark in the visible light can shine in the infrared. And this has a lot of advantages, of course. There are many, many applications of this. So infrared imaging is a powerful tool. And of course, it's a powerful tool for planetary science, because you can observe a body, such as a planet or a comet, even if the illumination conditions are very poor. Moreover, if you think of a planet like Jupiter, there is another advantage, is that you're not seeing the light which is reflected. You're seeing the light that Jupiter is emitting itself, which has much more information. So it's a much powerful information tool for studying a planet such as Jupiter. And also this light is not coming from the clouds, it's coming from just below the clouds of Jupiter. So it's bringing us much more information from Jupiter. Because in fact, this is a picture of Jupiter. It's a very cloudy planet. The bright regions are clouds of ammonium hydrosulfide, which are at the level of about 1 bar. Okay, at Jupiter, we don't have the sea level, of course. We have a conventional level, which is called the 1 bar level. At this level, or just below, we have those clouds. They are quite hot, so they are bright in the infrared. Above them, on top of them, 10 to 20 kilometers above, we have other clouds. And surprisingly, those clouds are made of a different chemical compound, which is called ammonia. And it's ammonia crystals. And those are cooled. So cold clouds, they are less emitting in the infrared, and they are darker. And that's the result. So you have dark clouds, ammonia clouds, on top of bright clouds, which are ammonium hydrosulfide clouds on the bottom. And because of this, because of the contrast of the emission, we can tell the morphology of the clouds, we can tell the motion of the clouds, because we can take multiple images, and so we can see if a cloud has moved. And as you know, because in fact, one of the results of Juno from the beginning of the mission, almost 3 years ago, was the fact that the Juno discovered that in the southern region of Jupiter, and also in the northern one, we have system of symmetric structures of cyclones, like this one. In the south, we have a central cyclone and 5 cyclones all around, so circumpolar cyclones, we call them. And of course, this was an amazing surprise, because it's a symmetric structure, and we were asking each other, oh, is this something by chance, or is it going to destroy after some time? Is it going to stay like this forever? Is it going to reorganize in a different symmetric structure sooner or later? And because of them, we were obviously looking to this southern polar region continuously, every orbit. I said, we have a camera. Unfortunately, we don't have a movie camera, so we're not able to stay on top and take pictures continuously. We can take pictures every time Juno brings us close to the region. So a picture every, say, 2 months. And we were asking each other, do you think it's going to happen now? Do you think it's going to destroy this symmetry? And then someone said, yeah, I think this orbit something will happen, maybe not. So concentrate your attention on the bottom right part of the screen. You'll see something is going to happen there. The symmetry seems to be broken every now and then. And so that's the point where we're expecting something to happen. Because in fact, you see now the pentagon is more likely an hexagon, and yep, like this. Now, in PJ23, just 1 month ago, we discovered that the symmetry changed itself. It reorganized it into something different. A system of 6 cyclones encompassing the central one. So actually, it's like having a family when there is a mother in the center and we have a new younger brother. This younger brother in the bottom right part of the picture is not as big as the others because it's new, However, the velocity are the same because Durham can also detect the velocity. Velocities are about 200 miles per hour, so it's on average, so it's a quite high velocity, comparable with the velocity we already detected for the others. And if you want to have an idea, this is the hexagon we can overlap on top. And if you want to have an idea of the size, then you can, for example, imagine you have the US in the center of the model. And the central cyclone is as big as the US. The younger brother is the same size of Texas or Italy, if you want. So what is the important in this? Okay, for me, this is the first time we're seeing a symmetric structure in the meteorology of the solar system changing itself to another symmetric structure, but different, from a pentagon to an hexagon. And this allows us to test models of the meteorology of a giant planet like Jupiter and test if those models are right. And if you have a good model, then you can do forecasting. That's the reason why I'm now leaving the ball to Cheng for modeling this description. Thank you.
Hello, everyone. So I'm a fluid dynamist doing simulations. And to me, these vortices are amazing features because from a fluid dynamic perspective, they shouldn't be there. There should be one single big polar vortex at the pole. If you look at planets in the solar system, for example, if you look at Earth or looking at Saturn, you would find only one cyclone at the pole, but not all of those things. So what happened? What's going on? And these are the questions that I want to seek for an answer. Then I can do some computer simulations. The computer simulation is like forecasting weather for Earth's atmosphere, but I'm now forecasting weather for Jupiter's atmosphere. So this model is not very sophisticated. It's similar to the model of weather forecasting people used in the 1970s. But I'm still using a supercomputer to do the simulations because I can go on a vacation and wait for a few days for the model to finish, and I can come back and to see the result. Right now, you are looking at the simulation from the pole that you're looking at from top to down. Now, the pole of the Jupiter is at the center of this domain. So I release the model. You can see that these storms becomes unstable, and they move around. They merge with other ones, and they collide. They kind of rotate, and eventually you will find that they didn't merge into a big giant vortex. Actually, they becomes a very regular pattern that rotates kind of rigidly around the pole. So it's kind of similar to what we have observed, but not exactly. So let me try a slightly different configuration. In the second configuration, where I can put those storms into the position that's similar to what we have observed. In addition to that, I put another one, like this outsider, around this latitude circle, so that I want to see how this outside vortex, how this outside storm interacts with the original family. And to the expectation, this outsider, that it drifts inward. But you can see that the original ones becomes unstable. They kind of merge, and they kind of rotate, and then you can find that originally there were 5, and now there are 4 storms left. So the 2 of them merged and end up with 3, and you can see that those 2 starts to rotate each other and trying to attractive. And then eventually, you will find that all those 3 storms disappear and end up with a big one. So this is what we should expect, what's going on at the polar region of a planet's atmosphere. But this is not Jupiter does. What Jupiter does is you have 5. And but because this is a computer simulation, and we can change parameters. So for example, we can change the thickness of the atmosphere we're modeling, or we can change the size of those storms, or we can change the strength of those storms. And trying to figure out what kind of configuration can produce situations similar to Jupiter. So in the last animation that I'm going to show you, you can see that in this configuration, there's a white zone around the center black one. So this white zone is kind of a buffer region. The buffer region that kind of protects the storm. And you can think of that the fluid in the buffer zone spins in the opposite direction to the fluid in the black zone. So it's like two gears that gear together, but they spin in a different direction. So in this case, when I run the model, this intruder moves in, but the original 5 is happily to welcome it. It opens up a gap, and then you can see that this intruder becomes part of the family. So, and initially this is not equal distance, but after a while, you can imagine that, okay, wow, these 6 storms arranged into a very regular pattern, an equal distance array surrounded the pole. So I think we now have a very realistic model that simulates what Jupiter's atmosphere do. Actually, we made this simulation before we actually made the observation, and well, seems Jupiter is heading towards what we expected. Although this simulation is produced very realistic morphology, but there's still a lot of things we don't understand, because right now this model is only 2-dimensional. It only simulates one layer of the atmosphere. We don't know what is going on at the depths, and that will tell us a lot of new information. So the next flyby will be after Christmas, and welcome to, maybe we'll have a great Christmas gift. Okay, so I will give my stage to Candy and to show you additional images from JunoCam.
Okay, thank you. I'm going to stay on the circumpolar cyclone topic just for one more minute. This is the JunoCam image. So now you're looking at visible light. And because of that, the dark shadow is the day-night boundary. We call that the terminator. You can see circumpolar cyclones number 4 and 5 just at the edge of that terminator. You can see the central one. And then the new one is the dark one. And it's not as big as the others yet. But I have to say it's been very suspenseful, because we had the 5 circumpolar cyclones, and there was a gap between number 1 and number 2. And it would get wider and narrower, and every perijove pass coming up on each one, we'd be asking ourselves, you know, what's it going to look like? Is there going to be something in the gap? Is the gap going to close? And so then, and this little guy has been hanging around for the last couple of flybys, we think. So on perijove 23, that pass, we finally saw this last one getting, or the 6th one getting into the group here. With that, I'm going to change gears, and I'm just going to share a tiny handful of the wonderful contributions that we get on our website. JunoCam is an outreach camera to promote citizen science. And I will just say the previous image was analyzed by 2 of our citizen scientists, and that picture came from John Rogers and Gerald Eichstadt. We have this one. This is from Bjorn Johnson. This is White Spot Z. It's about 11,000 kilometers across, so if I put the Earth in front of it, it would be covered up, but just barely. It's circulating above the north equatorial belt is prograde, the north temperate belt to the north is retrograde, and so it spins in between the two. This is one of my favorites of the Great Red Spot. The Great Red Spot, it perturbs the atmosphere in its latitude band. It moves at a slightly different speed relative to the clouds in its latitude band, and so it pushes up this amazing turbulence in front of it. This particular image was put together from 2 JunoCam images by Kevin Gill. And you can see so much beautiful structure in the turbulence in the Great Red Spot wake. You can also see a strand of the Great Red Spot itself seemingly pulled away, but maybe it relaxed back in again. This phenomena with pieces sort of separating has been studied by amateur astronomers for the last couple of years. And so We're in, of course, a lot of communication with the amateur astronomy community as we operate JunoCam. Now I'm going to show you two optical illusions. This is the shadow of Io on Jupiter. There's nothing really remarkable about that. Every time Io crosses in front of Jupiter and blocks the sun, you see a shadow on the disk of Jupiter. But what's different about this one is that this image taken by JunoCam, the spacecraft was very close, about 13,000 kilometers above the cloud tops. So we don't see all of Jupiter in this picture. We only see a curved sliver of Jupiter in this picture. So the proportion makes it look like the shadow is really giant, when in fact, it's the same size as ever, but you're missing most of Jupiter in the picture. This is another example of where you're only seeing a piece of Jupiter. And, oh, I'm sorry, let me just say, this was a contribution from Tanya Oleksuik. This one from Pratik Sarpal, he took a picture of one of our images of Jupiter that did not cover the entire planet, but he wrapped it around a sphere. And to me, it looks like a marble. In fact, if this was my marble, it would be my favorite marble. It would be my shooter marble, and I would never trade it to anyone. So sometimes our contributions are not scientific at all, they just bring us joy. This is one that we can use actually for scientific analysis. This is a picture of the turbulent atmospheric dynamics at about 50 degrees north latitude. This one is another one from Kevin Gill. He is one of our best, most prolific and very good quality contributors. And so you can see all the sort of turbulent swirls in the atmosphere. I'm going to draw your attention to the very tiny, bright white clouds. Now, I say tiny because they're on Jupiter. They're really not that tiny. They're about 25 to 50 kilometers across. But relative to white spot Z, which is 11,000 kilometers across, they're pretty tiny. And these tiny little clouds cast shadows on the atmosphere below. And so from that, we can get their altitude above the lower cloud deck. Turns out to be about between 4 to about 15 kilometers high. And we also know from the fact that they are high like that, we expect that they are composed of ammonia ice crystals. At a similar distance from the equator, but now in the south, around 48 degrees south, we have this image of some similar looking turbulent cloud features. And again, we have we call them the Popup Clouds, the tiny bright white ones. Those are what we call Popup Clouds. But in this case, you can see even more of the vertical structure. The orangish colored clouds are at the bottom of this vertical stack. How do I know that? I can see places in this image where the pastel colored clouds are partially obscuring the more orange cloud deck below. And then, of course, we've got our pop-up clouds. So there's a very three-dimensional aspect, and we can use this for scientific analysis to study the vertical structure of Jupiter's clouds. I'm going to end with this one. I consider this suitable for framing. This is an image that was processed by Gerald Eichstadt. He flattens out the illumination differences across the images. He actually does that for every JunoCam image we've ever taken. So of our citizen science contributors, he is our superstar. And then Sean Doran, who is a fabulous artist, takes what Gerald has done and turns it into a piece of art. Jupiter, of course, kind of cooperates. These storms are not unusual. This one's about 1,200 kilometers across, and there's quite a few of them at this latitude band, about 48 degrees north. And I don't know, I want to frame this. I want to frame this and put this on my wall. I'm going to conclude by just saying that at this point, we have over 5,800 contributions of processed images ranging from whimsical pieces of art all the way to ready for scientific analysis on our website that have been contributed by our citizen science community.
Okay, thank you, panel. We'll open the floor to questions from reporters in the audience.
Daniel Stolt, University of Arizona. To me, the most tempting question to ask is, do you think this might also explain the hexagon on Saturn?
Cheng.
Yeah, I think it's mostly a question for Chen, huh?
Yeah, okay. Yeah, so whether they merge or not depends on whether the storms or vortices, they have a buffer zone. And therefore, whether they have buffer zone actually in a three-dimensional model, it has to do with how the vertical motion of the air. And right now, we don't quite understand. Therefore, we need like more observation of the atmosphere at depths. So actually, I'm from the MWR team, and I'm very curious, and we're working very hard to get MWR measurement of the polar region so that it can tell us more about what's going on at the depths. And I think this is still an ongoing work, and it's open. And I don't know the answer right now, but we will in the future.
And I'll just point out that with each orbit, our perijove moves a little bit further north. So the MWR measurements are able to do high-quality measurements a little bit further north as each orbit goes around. If we stay in orbit long enough, if everything keeps working, if we get an extended mission and so forth, eventually that perijove will get far enough north that MWR can get really good data over the circumpolar cyclones.
Harvey Lyford, freelance for Dr. Levin. You just referred to a possible extended mission. My question was going to be, assuming you will have one, which I do, what are you thinking of doing that you haven't done before? Or is it just more of the same? And second question, I may as well just throw it in now. When the mission was originally conceived, I know it was supposed to be shorter orbits, but did you not anticipate the possibility that there would be eclipses of Juno? It seems to have been like a crisis.
Well, of course, we anticipated this eclipse well in advance. It was a crisis, but it was a crisis a couple years ago and we had time to figure out what we were going to do. So by the time we got to it, we had the plan in place. We knew we were going to be able to avoid this eclipse. First of all, thanks for assuming we're going to get an extended mission. I'd certainly love for that to occur, but we're still in our prime mission. Doesn't end till 2021. We are working on what the proposal would look like for an extended mission, talking to NASA headquarters about exactly what they'd like to see from us and when in order to show it. So I can't really say, well, here's all the science we would do. Not that we haven't thought about it, but we're not ready to write that proposal. I would say some of the science is going to be things that are continuation of what we've been doing, but doing it better. Much of it, if we get an extended mission, is bound to be exploring the discoveries that we've made. We've discovered an amazing number of things about Jupiter. Our catchphrase within the team is it's a whole new Jupiter. Almost every experiment has found a surprise. So obviously a lot of those need follow-up, and some of that follow-up might be better in an extended mission than in the current main mission, prime mission.
More questions from reporters in the room?
I'm sorry, I'm realizing, and maybe I didn't quite answer all of what you asked about avoiding the eclipse, right? The 53-day orbits, because they're longer, meant the same number of orbits takes longer, so you get to the time where there's going to be an eclipse. When it was a shorter mission with the same number of orbits, you wouldn't last long enough to have an eclipse.
More questions from the room? All right, we have a few questions from folks watching online.
So Rick Lovett, freelance, asks, can you explain why, in simple conceptual terms, why the storms don't merge into one, and how do they die? As in, why hasn't it accumulated 10 or 15 or 20?
Okay, so in simple terms, it is the buffer zone that prevent the merge, kind of push them away from each other. And but turbulence will eventually erode the buffer zone. So it's kind of, it takes time to erode the buffer zone, and once the buffer zone disappeared, two of them will merge. So it's kind of a equilibrium between how fast the buffer zone is eroded and how fast the small storms is supplied to this system. Like Candy has showed that actually these things, there are a lot of them outside of the observable region, but they cannot move in because the space is occupied. So they only move in when they are weak and they kind of open a gap, and then the new one can come in.
Erica Carlson with Discover and Astronomy magazines asks, what changed in the simulations that allowed the new storm to join in the others without disrupting the arrangement, and what future work needs to be done to test whether what happened in those simulations is indeed what's happening at Jupiter's south pole?
Okay, so what changed? So I have shown two simulations. One of them is that they all merge into a big one, like Saturn or Earth, and the other one they don't. What changed is basically I changed the width and the strength of this buffer zone. So I can make the buffer zone very weak, and in this case they will merge. Or I can make it very strong. In this case, they will repair each other. But like I have explained before, the buffer zone is kind of two-dimensional projection of a three-dimensional feature. And what three-dimensional means that there's vertical motion involved in there, but it's not in the simulation. So in the future, of course, we can have a three-dimensional model, but three-dimensional model involves more parameters that we don't understand. So we need new observation to give us a more constraint on the three-dimensional structure of that. And I think from my perspective, the new three-dimensional information has to come from the MWR, because MWR can sense very deep, like to 200 bars. That will be very valuable information we can gather in the future.
And then Monica Young with Sky and Telescope asks, what originally causes the vorticity that makes these storms? Is it just Jupiter's rotation along with turbulence?
Okay, so the vorticity it can come from a lot of reasons. For example, if you have temperature gradient, or if you have one place that is warmer than the other place, and then atmosphere can meander, and one of the meandering, it can pinch off, that gives off a vortex. Like the crucial or like the ocean current, that it always sheds off vortex. That's one of the reasons. The second reason is because Jupiter is kind of warm planet, it has internal heat. So the internal warmness of Jupiter will cause thunderstorms. The thunderstorm can also create a vorticity. The third one is Jupiter is cooling off from the space. So you can have cold air sinks to the interiors of Jupiter. Like the sinking of the cold air can also create vortex. So there's millions of reasons that you can create of different various kinds of vortices.
And then Rick Lovett has another question. Since the 53-day orbit stuck you on a slower observation cycle, does this turn out to be a great gift from that by extending your viewing time?
For a lot of things, it's a great gift, I agree. Not so much viewing time in the sense that when we go past Jupiter every 53 days, that perigove pass is very similar to what it would have been in a shorter orbit. But it's a gift of time in the sense that Jupiter has time to move around the sun, so the orbit shifts to different places, and we see different things that perhaps we wouldn't have seen. And anything that's time dependent, anything that's changing with time, now instead of a couple of years to see any changes, we have many more years. Of course, it costs NASA money to do that. We would not have chosen this orbit size if we didn't have to, just because it's more expensive.
I have one more comment. It's actually good in my perspective to study the polar vortices, because if you look at movie carefully, these polar vortices actually will precess around the pole, but the precession is kind of slow. So we need a longer orbit to measure the precession of those polar vortices.
That it from the chat? Okay, great. More questions from reporters in the room? Anybody think of anything? All right, then let's thank our panel. Thank you all for being here. I'm sure they'll be here for a bit longer.